Welcome to Math 31. This is the first lesson in Unit 5, which is Extrema and Curve Sketching. So I'm going to do introductory work on first derivative analysis involving the first derivative test. A lot of what will be covered in this would be variations of things we've observed before, but now it gets formalized and we get much stricter in how we look at things, because we're going to be doing some fairly intense graphing soon, and we have to make sure that we're paying due diligence to all the details involved with some of the complexities of graphing. So first derivative analysis. If you were to consider what appears to be just a regular function there with x1 and x2, 2 points on the curve, and I'm going to indicate on the y-axis that this would be f at x1, so the y value corresponding to that x value, and then this is f at x2. Then, make what appears to be a fairly obvious point, that a function is increasing in interval if, when x1 is less than x2, which it is in this case, f at x1 is less than f at x2, which it is in this case as well. So we would say that this is an increasing function. Now most people, when they inspect a graph, they would come to the same conclusion without any of the fancy talk. They would say it's rising, so therefore the graph is increasing. And that really is all you have to keep in mind. Now the other point is that a function would be decreasing in an interval if, when x1 is less than x2, which it is in this case, f at x1 is greater than f at x2. So that does not match our graph. It's a true statement, but we actually have an increasing graph, at least for this interval x1 to x2. So obviously within a function, it may change from increasing to decreasing several times. So you're always dealing with not the whole graph, but rather intervals. So I'll just say that this graph is falling. So I hope that that information doesn't shock anyone. Then if you were to consider this function below, if we were to analyze the intervals and where this thing is increasing or decreasing, just going to make these these points. In the interval negative infinity to 1, let's say, non-inclusive, we would say that the graph is increasing. And moreover, if you were to consider the slope of the tangent line at all points is going to be positive. So this would make sense. F prime at x is greater than 0, or I hope it makes sense. The first derivative would be positive. And then right at x equal 1, we would say that f prime at x is equal to 0, a turning point. So the first derivative, the slope of the tangent line is 0, so the first derivative is equal to 0. And then for these other intervals, all the way down, or this next interval all the way to 4, we could say 1 lower limit, 4 upper limit, non-inclusive. The graph is decreasing. And f prime at x is going to be negative, so less than 0. And then so on. At x equal 4, f prime at x is equal to 0 again. And then from 4 to positive infinity, upwards forever, we would say the graph is increasing, is rising, as well f prime at x is going to be greater than 0. So the first derivative would be positive. So fairly obvious points. Now to summarize all this, can refer to the first derivative test, which states that if the first derivative is greater than 0, that is positive, for all x values within that interval, then the function is increasing in that interval. Seems reasonable. Same thing if the derivative is negative, the function is decreasing in that interval. Okay, we saw that in the previous one. Here's the point that's maybe a little debatable. If the derivative is equal to 0, then this x value is a turning point. And then I put in probably, because that isn't ironclad. That's not a guarantee. So we'll have to spend some time getting clear on this point. Certainly it was true in the previous graph. Won't always be true, though. So you want to file that information away someplace. So for the next batch of questions, we just want to find the intervals where the function is increasing or decreasing. So a basic polynomial function like this. So it all begins by taking the derivative, which isn't that difficult in this case. F prime at x is equal to 6x squared plus 6x minus 12. And then we use interval analysis, which I'll call in this case first derivative analysis. And this will tell us where the graph is increasing, where the graph is decreasing, and where it's actually having what appears to be a turning point. So the method would be factoring this if it does factor. So we would initially take out a factor of 6. Do not divide out the 6 because it's not equal to 0, so you cannot just get rid of it like that. And then this will take us to f prime at x is equal to 6 times x plus 2 times x minus 1. And then we do interval analysis. Now we have these three factors, 6x plus 2, x minus 1. So this takes us to where we've been before. That is, we're working with a number line. So I'll write that out to the side. F prime at x is equal to 6 bracket x plus 2 bracket x minus 1. Now the issue is the 6, because the 6 is a positive number, so you may recall from the first unit that you don't need to include that in the interval analysis because it's always positive. It does not affect the signs. But we must have the other factors, and then f prime at x like that. And then we locate the points where each of the factors are equal to 0, so x plus 2 would switch signs at negative 2. And then x minus 1 would switch signs at x equal 1. And then we note the behavior. At x plus 2, that factor is positive when x values are greater than negative 2. And negative for values less. And then x minus 1, positive to the right of 1, negative to the left of 1. So f prime at x, the derivative, is positive to the left of negative 2. It's negative between negative 2 and 1, and then it's positive when you're to the right of 1. So what I usually do to indicate the actual nature increasing or decreasing is I put an arrow upwards in the positive, arrow downwards in the negative, arrow upwards in the positive. Then to formally note where it's increasing, I would say in the interval from negative infinity to negative 2, as well, union with the interval from 1 to positive infinity. And then this graph is decreasing between negative 2 and 1. So that's all you're really doing with these problems. Now obviously they get more complicated when you get away from polynomial functions because the graphs and the derivatives are more complicated. But here's what we get in this case if we observe the graph, and it seems to match with what we calculated. To the left of -2 it's increasing, to the right of 1 it's increasing, and then between -2 and 1 it's decreasing. Number 2. Here we have x plus 1. Now this is going to be more complicated to differentiate. I'm going to recommend the quotient rule. So I would go u is equal to x. So u prime is equal to 1. And by the way, as always, stop me at any time and solve this question on your own. V is equal to x plus 1. So v prime is equal to 1. And y prime with the quotient rule is equal to u prime v minus u v prime all over v squared. So y prime would be equal to 1 times v, which is x plus 1, minus u, which is x times v prime, which is 1. So I'll just write that as 1x. And this is all over x plus 1 squared. So therefore, when we mop this one up, the first derivative is x plus 1 minus x, and we're left with just 1 over x plus 1 to the 2. So I did that quickly, but that's the situation. Now, if we take a look at our number line again, we could simplify this method, but I'm going to include the 1. And I know you're thinking, well, why bother? Because it's always positive, and you're right. I'm just doing it because. And then f prime at x like this. And you're also thinking perhaps, well, x plus 1 squared, can I write that as x plus 1 and then another factor of x plus 1 below it? Of course you can. It's easier, though, to do it together when you have something squared, and partly because of the sign. Now, in all the fuss, I had neglected to make this very obvious observation earlier that x cannot be equal to -1 on the original graph. Now, when I do the analysis on this, I really recommend noting that -1 on the analysis part. So I'm going to put a dotted line through that. Now, I'm not expecting anything to really change there because it's not a 0 for any factor. I guess it is for x plus 1 squared, but it doesn't exist on the graph. But let's see what happens. So I encourage you to put that value there. It's not necessary, but you will see when we get to the answer part, if you fail to put it there, it's possible to overlook something. So with interval analysis, I really encourage you to put as much information as you can, just so you don't have to keep track of things. Now 1, this factor is positive everywhere. X plus 1 squared, well, you pick any x value, add 1 to it, and square it, it's going to be positive. The act of squaring will make it positive. So this is what we get. So it means that our derivative is actually positive everywhere. So there was no direction change at -1. Draw the little arrows up and up. But in terms of the increasing and decreasing, I'm going to write this, I'm going to bring up well, no, actually, I'll do it first. I'm going to write it down below. This thing is increasing and the intervals from -infinity to -1, and then in union with -1 to positive infinity. So it would be a mistake to say that it's increasing everywhere because of the hole in the graph at -1. And then the graph itself will support this because we end up getting a reciprocal type function like this. So if you graph it yourself, you should get something pretty similar to that. Now, one thing that is noteworthy here is that if you did actually compare two x values, say these two that I've got indicated, so you could call this x1 and x2, you know, based on our original observation at the start of the lesson, we have this statement to be true. x1 is less than x2. That's correct. And then there's f at x1, and then there's f at x2. And if you thought about it, even though x1 is less than x2, f at x1 is greater than f at x2. So this suggests the graph is decreasing because the y value is decreasing as the x value increases. Now, it's obvious from the graph that the reason that's so is because of the asymptote at -1, so that the graph is actually you know, starting over again at the bottom. So this is just a curiosity, but it also is a reminder that if you are trying to determine whether a graph is increasing or decreasing over an interval, it's not wise just to plug in values and compare the x values and compare the corresponding y values, because it could be misleading, as it is in this case. If you just subbed in x1 and x2, compared f at x1 and f at x2, you would conclude that, that it's decreasing, and it's not. So be careful. I doubt if that'll be a big issue, but that's something to give some thought to in the next little while. Next one. So y is equal to x plus 1 over x. Well, this one differentiates pretty easily. We would first off write this as x plus x to the -1. So therefore y prime is equal to 1 minus x to the -2. So we could then write this as f prime at x is equal to 1 minus 1 over x squared. You'll notice that for these ones, I prefer not to use Leibniz notation. It works well for the substitutions and just the way we indicate things. So it's I'm keeping it like this. Leibniz notation would be fine, just a little more awkward. Now the thing is as well, we can not have x equal to 0. So x does not equal 0. And as we go on with this one, also should be aware that it's a bit of a problem in terms of interval analysis. If you think back to Unit 1, it might occur to you that the best approach would be to get an LCD. When we would have two polynomials being subtracted, or two rational functions or algebraic expressions, we would usually get a common denominator. Because that makes the analysis much easier, so that we can actually compare a numerator. We have it in terms of a factor over a factor. So we have to multiply by x squared for that first term, and we get this. If you did not do this, you would have some difficulties in the analysis part. So x plus 1, let me rewrite this, f prime at x is equal to x plus 1 times x minus 1 divided by x squared. And remember, you want to have this thing broken down as far as you can. So, our one factor is x plus 1. Our other factor is x minus 1. Then we have an x squared factor, and I guess in all this I cheated myself out of a line. But here's f prime at x. Now, the points, the zeros where the factors change sign, first off -1 for the first factor. Don't forget about 0, because that, if you set x squared to 0, that's where it would be equal to 0. But more importantly, that's the inadmissible value. And then 1. Like that. Because we want to be aware that something is happening at x equals 0. And it's very possible that there could be a change in the graph right there. So putting those non-permissible values is an excellent idea. And x plus 1 is positive when we're to the right of -1. So nothing unusual happening with this analysis. You've done much more complicated ones, and you will be doing more complicated ones in the future. For x minus 1, it's positive to the right, negative to the left. And then for x squared, well, any x value will be positive everywhere when you square it. So I said every x value, but for every x value, when you square it, you'll get a positive number. So this gives us a positive there, gives us negative there, gives us negative there, gives us positive there. So according to this, the function is increasing in the interval negative infinity. So actually put your arrows in so you can read the graph easier. This makes it easier to see what's going on, so you can just visually do a quick, taking stock of. So from negative infinity to negative 1, it's increasing. It is also increasing from positive 1 forever upwards. And then the function is decreasing from the interval negative 1 to 0 in union with 0 to 1. So two separate intervals. I didn't bother graphing this one, but I would encourage you to do so because you do get an interesting graph. So y1 is equal to x plus 1 divided by x. So you should end up getting basically what it looks like the similar graph to the previous one, except it's going to be rotated slightly. And make sure that if you are using your graph to compare this, that you graph the function itself, the original function. Do not graph the derivative. Now let's just do this one more problem. This is also not new. You've done these before. But if you were given the derivative and you want to sketch the original function. So, well, we've done, okay, let me back this one up, where we've done the reverse of these ones before, more likely. So we get this for a graph. There is our derivative, and we want to make enough sense of this so that we can graph the original function. I guess I gave you some space. Now, I also encourage you to stop and to do this on your own and then compare what's happening with it. And what's interesting with this graph is you have to think backwards with it pretty much, because if you take a look at the intervals, I guess, with this one, from negative infinity on this function all the way to 1. So I'm selecting this point right there, the x-intercept. The graph, f prime at x, is positive. So the derivative is above the x-axis. So therefore, if the derivative is positive, it means f at x is increasing. So we're thinking backwards on this one. So anywhere that this derivative is above the axis, it means that the first derivative is positive. Therefore, the original function is increasing. So we're paying attention to the x-intercepts. Just like in the interval from 1 to 3. Now before that, we should be aware that x equal 1, the derivative is equal to 0. So this is a turning point, probably. It's safe to say in this case, but we will eventually nail that down better. And then from 1 to 3, the derivative is negative. It's below the x-axis. So therefore, we have the f at x decreases. And then x equal 3. The derivative is equal to 0. So this is a turning point, probably. And then we go from 3 to positive infinity. The derivative is also above 0, greater than 0. So the original function increases. And with this information, we should be able to transfer it to a clean graph. Now this is a quadratic, so you might be, if the derivative is a quadratic, it may have occurred to you that the original function would have been a cubic. So that's also true. But let's take this one. So we know that x equal 1 is a turning point. We don't know about the y values. I'm actually going to scrub them out because we don't need them. But at x equal 1, we've got a turning point. The graph is increasing until we get there. So I'm not going to take any information about x and y intercepts or anything. We'd need more information to get them. But the graph is increasing until we get to 1. Then it's decreasing. And then it has a turning point at 3 and then starts increasing again. So we end up getting something like this. So y equal f at x. So it's a poor sketch, really, in the terms of not knowing where the x-intercepts are. But these points there, we do have. So we do know where it's turning. So we know where the function is increasing or decreasing. And the turning points. So we can get a rough sketch. So I'll leave you with that. The next lesson we'll go a little bit further into this area, but more dealing with the extrema values themselves, that is the maximum and the minimum. Thank you for your time.